You know that feeling when some new design software or method just lands on your desk
Oh, yeah.
and it feels less like this cool new tool and more like, yeah, like you're staring at a spaceship dashboard you have absolutely no idea how to fly.
Been there. Definitely.
We've all been there. So, welcome to the deep dive. What we do here is take the raw source material, and today that's recordings from a really detailed class workshop, and we basically boil it down.
Yep. Distill it to the key stuff you need to know.
Exactly. Think of us as your shortcut to understanding, minus all those hours trying to figure it out alone.
Precisely. And today, we're diving into the data behind the design. Specifically, we're going to look at vector operations, how surfaces get made, analyzed, all within Rhino and Grasshopper. And yeah, our source is this pretty comprehensive workshop recording.
So maybe you're already using these tools, or maybe you're getting ready for a project that needs them.
Or maybe you're just curious, right?
Yeah.
About what's possible without getting totally lost in the technical weeds.
Yeah, this deep dive is definitely for you. We're going to try and make it super clear, engaging.
And I'm here to help connect those dots, explain the sort of why behind these digital techniques.
Perfect. Okay, let's get into it then. So the instructor in the workshop, they start off by pointing everyone to a GitHub repository.
Right, which is loaded with code examples. It's kind of like getting the cheat sheets early on.
Yeah. And one of the first things they look at is this Jupyter notebook environment.
Which is interesting because it's this dedicated space, right? It's separate from Rhino and Grasshopper.
Okay.
And it lets you really kind of focus on practicing the Python code itself. Get comfortable with the basics before you even think about integrating it into your designs.
Right, get the fundamentals down first. And they show this with the function service example.
Yeah, where you can basically type in a mathematical equation and just run it, see what happens.
Cool. And you define things like the domain, that's your start and end range, the U.
And the resolution, which is like how many steps you take within that range.
Like setting the quality level.
Yeah.
More steps, more detail.
Exactly. Higher resolution means, a smoother result, generally. Fewer steps, it might look a bit more jagged or blocky. Depends what you're making.
Makes sense. Then they mention NumPy, which sounds like a Python thing for handling lots of numbers efficiently.
Yeah, NumPy is huge in the Python world for anything involving arrays or big lists of numbers. It lets you do calculations on everything at once, basically in parallel.
Yeah.
Super fast.
Okay.
Now, they might not use it explicitly in every single example here, but it's kind of fundamental. If you start doing more complex stuff, bigger data sets in your designs, NumPy becomes really essential.
Gotcha. And we actually see the result, right? They show how a function creates this like wave surface visually. Even though it's just code, you instantly see, oh, okay, you can generate complex shapes this way.
Yeah, and they show simple stuff too, like making a sphere or a cylinder just with code in that environment.
That whole playground idea seems really key then.
It really is. It lowers that barrier to entry for programming, lets you see that direct link. Code becomes form.
Yeah, without needing the whole Rhino Grasshopper interface right away, just building that core understanding.
Exactly.
Okay, so then moving into Grasshopper itself, the focus shifts to actually creating surfaces.
Right, and one method they walk through uses nested loops, double for loops.
Okay, nested loops, like one inside the other.
Precisely. Think about laying out tiles on a floor. One loop does the rows, the inner loop does the tiles within each row.
Okay. I get that.
So in the code, these loops are just systematically calculating point positions in 2D. You give it the X and Y limits, the resolution.
And it just plots out all the dots on a grid.
Exactly. Laying the groundwork.
And then the Z value, the height that makes it 3D, that comes from the X and Y coordinates using some math function.
Yep. In this case, it's the function that creates that wave shape we saw before. The math dictates the form.
That connection from the flat XY grid to the 3D Z value, that's kind of the core idea, isn't it, for making surfaces mathematically?
It really is fundamental.
Now, here's where it got kind of interesting for me. They talk about the difference between RhinoCommon and RhinoScript syntax for actually making those points.
Yeah, that's an important distinction.
RhinoCommon apparently gives you the actual geometry object, the point itself. So you can just grab the X, Y, Z straight away.
Correct. It returns the point object directly.
Whereas RhinoScript syntax, it gives you a GOD, which is like a barcode.
Yeah, exactly. Think of it as a unique ID number for every single thing in your Rhino file. It doesn't give you the point itself, just its address, basically.
So you need an extra step. say, hey, Rhino, what geometry belongs to this barcode?
Pretty much. You have to use the GeoID to then retrieve the geometry object if you want its coordinates.
Okay, so RhinoCommon is more direct, maybe better for really complex stuff, and RhinoScript syntax is maybe simpler for everyday scripting.
That's a good way to put it. RhinoScript syntax is often seen as more approachable, especially for beginners. RhinoCommon offers deeper control.
It's like getting the treasure chest, the GeoID, but needing the key, that extra step to see the treasure, the coordinates.
Case analogy, yeah.
So then they show how you take all these points, maybe made with RhinoScript syntax, and use the add curve function to, well, draw a line through them.
Yep, connect the dots.
And if you do that for rows and columns of points, you get this network of curves, right? U and V curves.
Exactly. That forms the kind of wireframe skeleton of your eventual surface.
And then, boom, they show the lofted surface function, which sounds like a pretty straightforward way to just
Drape a surface over those curves.
yeah, like stretching fabric over the wireframe.
Lofting is super common, very intuitive. The software figures out how to blend between the curves you give it.
They also quickly mention another way, making a surface directly from a grid of points. They kind of park that idea for later, though.
Yeah, it hints that curves aren't always necessary as the middle step. You can sometimes define a surface just by its points.
Okay, so now we have a surface. The workshop then gets into understanding its properties, like U and V domains.
Right, so think of UV coordinates like latitude and longitude, but for your custom surface.
Okay, a map reference.
Exactly.
Uh-huh.
Two numbers, U and V, let you pinpoint any location on that surface, no matter how curvy it is. The U and V domains are just the overall range, like the minimum and maximum latitude and longitude that define the boundaries of your map.
So it maps a sort of flat rectangle onto the 3D curved shape.
Precisely. And these UVs are crucial for doing stuff on the surface, placing things, checking curvature, dividing it up.
And you can project a point onto the surface to find out its UV address.
Yep, find exactly where it lands on that surface map.
Very cool. Then they talk about finding the area and the centroid. That's the balance point, right?
Geometric center, yeah. Where it would balance perfectly if it were a physical object.
And RhinoScript syntax has functions for that. Surface area, surface centroid. Seems easy enough.
Yeah, those are pretty direct. Essential calculations for lots of design analysis like material use or stability.
But they also mention this other way, almost like a low-tech way. Projecting loads of points onto the surface and just averaging their 3D positions to estimate the centroid.
Huh. Yeah, it's more of a conceptual thing.
Would you ever actually do that?
Probably not in practice, no.
Mm.
The built-in function is way faster, more accurate. But doing it manually, like that really shows you what a centroid is. It's the average location of all the points making up the shape. It's a good way to understand the underlying math.
Ah, okay. Makes sense conceptually. Right, then the workshop pivots to vectors, which
All right.
brings back fuzzy high school physics memories for me.
Huh, yeah. But here they're super practical. A vector is just direction and magnitude. An arrow, basically. Length and direction.
But the key thing, they say, is it needs a starting point, an origin.
Absolutely crucial. Without an anchor point, a vector is just an abstract direction and distance. It doesn't exist in space until you say where it starts from.
They use this example, extruding a rectangle towards a point.
Right. And they explain that the point itself can be seen as defining a vector from the world origin, 0, 0, 0, 0, to that point.
So the point's coordinates tell you the direction and distance to extrude.
Exactly. The rectangle gets pushed along that imaginary arrow from the origin to the point.
And they really hammer home that the starting point of the object matters.
Oh, yeah. Same vector applied to two different objects. They move the same direction, same distance, but they end up in different final locations because they started differently.
The vector is the change, the displacement.
Precisely. Relative to the start.
Okay. Then they circle back to putting points on a surface using UV values again.
Using those normalized 0 to 1 values.
Right. The latitude and longitude between 0 and 1. And you multiply those by the actual U and V domain lengths of your surface.
Yep. So if your U domain runs from, say, 0 to 20, and your V domain from 0 to 10.
A UV coordinate of 0.5, 0.5 would land you at U10, VO5 on the actual surface.
Exactly. It's a consistent way to find any specific point, even on really complex, wiggly surfaces.
Which leads into this idea of a surface frame, a local coordinate system right there on the surface.
Yeah, this is super powerful. At any single UV point on your curved surface, you can define its own little local X, Y, and Z axes that are perfectly aligned with the surface at that spot.
Whoa. Okay, why is that useful?
Oh, for loads of things. Orienting objects precisely on the surface, analyzing things locally. It gives you a reference system that respects the surface's curvature at that point.
And to get that frame, you first need the U and V domain, the overall size of the surface map.
Correct. Minimax U and V values.
Then you use that 0 to 1 normalized UV value, multiply it by the domain length.
To find the exact location along U or V, converts the percentage into a real distance on the surface.
So U at 0.5 times a domain length of 20 gets you 10 units along U.
Yep. And once you have that specific UV point, you can then ask for the surface frame. You can get its x-axis vector, for instance.
Which tells you the primary U direction of the surface right there.
And they remind us that a plane in 3D is just an origin point plus XYZ vectors. So the surface frame is essentially giving you a plane that's tangent to the surface at that UV spot.
Okay, tangent plane. Got it. Moving on to more analysis. Normals and curvature. Normal, I kind of know it's the direction the surface is facing, right?
Pretty much. The workshop explains how you get it.
Yeah.
You find the U to V tangent vectors. At your point, those lie flat on the surface in the U and V directions.
Okay.
Then you do a cross product. It's a specific vector math operation between those two tangents. The result is the normal vector.
The one sticking straight out, perpendicular.
Exactly, 90 degrees to the surface at that point.
And they talk about normalizing it, making its length equal to 1.
Yeah, creating a unit vector. Super useful when you just need the direction, not the length, like defining up relative to the surface.
And then you can scale that unit normal to push things off the surface by a specific distance.
Precisely. Offset points, offset whole objects.
Then things get a bit more complex. Principal curvature, mean curvature.
Yeah, these describe how the surface is bending at that point, how much and in which directions.
And Grasshopper has components that just give you these values?
Thankfully, yes. Makes it much more accessible. Principal curvatures are the max and min bending. Mean curvature is the average of those two.
And Gaussian curvature, that's multiplying the two principal ones.
Correct. And the signs of mean and Gaussian curvature tell you a lot about the local shape.
Right, like convex, bulging out like a ball.
Or concave, dented, and like a bowl.
Or developable, meaning you could flatten it like paper.
Exactly. Developable surfaces have zero Gaussian curvature. Think cones, cylinders, flat planes. So these curvature numbers are like diagnostics for your surface.
Highlighting potential stress points or areas that might be tricky to make.
Precisely. They even mention you could calculate all this yourself manually, with tangents and normals if you really wanted to.
Wow, okay. Advanced level.
Yeah. And they touch on visualizing curvature with colors on the surface, which gives you that instant visual feedback. Red for high curvature, blue for low, that kind of thing.
Then there's surface subdivision, breaking one big surface into smaller bits.
Yep, into smaller connected patches.
Yeah.
Useful for more detailed analysis, or maybe refining just one area, or for manufacturing if you're working with panels.
And curvature plays a role here too, like you might subdivide more finely where it bends a lot.
Often, yeah. To capture the shape accurately, or deal with material limits, which leads into minimal surfaces.
Like soap films.
Exactly. Surfaces that naturally minimize their area for a given boundary. Mathematically, they have zero mean curvature.
And they compare it to making a curve straight iteratively, so you adjust the surface bit by bit until it settles.
That's the idea behind some methods, yeah. Iteratively relaxing it towards that minimal energy state.
And this all connects back to real-world making, right? Fabrication.
Absolutely.
Yeah.
Material bending limits, breaking points, those are directly related to the curvature you design. It's not just abstract math. It dictates if something can actually be built.
Stops you designing impossible objects.
Hopefully. They also give a quick shout out to tools like Millipede and Grasshopper, which are specifically for exploring minimal surfaces and physics stuff.
Okay, shifting gears slightly. Back to making surfaces, but this time from curves. Lofting and extrusion.
Right. We saw lofting briefly before making a smooth surface between profile curves.
And the loft component has options. Tangent, normal.
Yeah. Controls for how smooth the transition is at the input curves. Continuity settings, basically.
Then extrusion, taking a 2D shape and pulling it into 3D.
The classic way to make solids or surfaces that cover a few types. Extruding along a vector is common, defines direction and distance.
Like using vector 0, 0, 10 to pull something straight up 10 units?
Yep, along the z-axis. Or you can extrude to a point.
Ah, so the vector is kind of implied from the curve towards that point. Gives you tapered shapes.
Exactly. And you can also extrude along a path curve, so the shape follows some complex 3D trajectory.
And again, these visual tools in Grasshopper have underlying code functions, right?
Yeah.
Like extrude curve, add loft.
The API function's doing the actual work behind the scenes. It's good to remember that connection.
Okay, last big geometry topic, Boolean operations. On solids or Breps?
Brep boundary representation. It's just how the computer understands a solid object by defining all its bounding surfaces.
Got it. And Booleans are union, subtract, intersection.
The fundamental ways to combine solids. Union merges them. Subtract cuts one out of another. Intersection finds only the overlapping volume.
Like digital carving and gluing.
Pretty much. Essential for making complex forms by adding or removing simpler shapes.
I show simple examples, right? Merging cubes, cutting a hole with a cylinder.
Yeah, basic stuff to illustrate the concepts.
Yeah.
And again, these have corresponding RhinoScript syntax functions like Boolean union.
It seems like these Booleans are super powerful for creating really intricate stuff.
Definitely. Things that would be very hard to model just by pushing and pulling surfaces directly.
And they make the point that understanding how to break these solids back down into curves and points is key for manipulating them later.
Yeah, understanding the underlying structure helps you control it better.
So to help you actually use all this stuff, they really push the API documentation.
Oh yeah, the docs are crucial, your ultimate reference guide.
Explains every function, what it needs, what it gives back, the
Yeah.
instruction manual for everything.
Mm-hmm. And they show how to find it online, but also the help panel right inside Rhino.
Oh, convenient.
Super convenient. You can just search for a function name like add point or lofted surface and get the details right there. It's like having an expert on call.
Invaluable for learning and troubleshooting.
Absolutely.
So bringing it all home, the workshop really encourages you, the listener, to think about how all these concepts apply to your own design work.
Yeah, how can you use vectors, UV spaces, Booleans to tackle real challenges? Creating specific shapes, adding features, analyzing forms.
Look at stuff around you, everyday objects, and try to imagine the digital steps, right? The vectors, surfaces, cuts, joins that could build them virtually.
It's a great exercise. They also briefly mention computational thinking, breaking problems down logically, and why understanding data structures becomes more important as you do more complex things.
Thinking like an algorithm, almost. Understanding how the information flows.
Exactly. That foundation in data, like they explore the workshop, it really unlocks new ways to think about design.
So, okay, that was our deep dive. We've covered some really core ideas. Vectors, surfaces, analysis in Rhino and Grasshopper, drawing from that workshop material.
Yeah, seeing how code, geometry, and your actual design intent are all linked up.
And for you listening, we really hope this gives you a solid footing with these tools and ideas.
You should have a clearer sense of what's possible now, feel a bit more empowered to explore, maybe tackle challenges with this new, data-driven perspective.
Definitely. So here's a final thought to chew on. How does this ability to computationally define geometry, to manipulate it so precisely, how does that open up totally new design avenues?
Things like generative design, where algorithms help create options.
Yeah, or optimization based on performance data. Creating forms we couldn't even have sketched before. What new kinds of exploration become possible when you start thinking in terms of data in algorithms?
It's a big question. We really encourage you to dig into the Rhino and Grasshopper documentation. Try out examples if you can. Look for tutorials online. It's a continuous learning path.
Super rewarding, though. Thanks for taking this deep dive with us.